So, Chapter 5, Brakes and Clutches, Part 1 of 2, Brakes. The second part we will see about the clutches. So, what is a brake? Brake, we have seen commonly in our automobiles. Brake is defined as a mechanical device which is used to absorb the energy possessed by a moving system or mechanism by means of friction. And the primary purpose of brake is to slow down or completely stop the motion of a moving vehicle. So, purpose of the brake is to slow down or completely stop the motion of a vehicle. Such kind of a device is called a brake. So, how does a brake work? Brake works by means of a artificial resistance that is applied on a moving machine member, and different types of brakes. The different types of brakes are used in different applications. Based on the working principle, brakes can be classified as mechanical brakes, then we can classify them as hydraulic brakes, then we have electrical, basically eddy current, then magnetic brakes and electromagnetic brakes. These are the different types of classification of brakes. So, we will see about mechanical brakes. So, mechanical brakes are basically working principle of a mechanical brake is on frictional resistance principle. In mechanical brakes, the artificial resistance created using frictional contact between a moving member and a stationary member stops the member. That is, if you have a moving member like this which is rotating at some speed, when you apply brake, you are actually bringing a stationary member in contact with this moving member, and when this comes in contact with the moving member, it exerts a force which is a normal force, which will be pressure times area. So, if I say that if this small area is dA and if P is the pressure exerted onto the moving member, then the normal reaction that comes in contact will be P into dA. That will be the force acting on this moving member due to this stationary member. And when this normal reaction is there, when one member is rotating and another member is stationary, friction comes into play, and the frictional force due to this small normal force will be given as mu times dN, which will be nothing but mu times P into dA. This is the frictional force which is causing the moving member to stop, or this frictional force, if this is the direction of rotation, the frictional force will be in this direction. This will be dF. That's the frictional force due to this contact force P into dA. This frictional force causes the rotating member to slow down or completely stop, and the braking torque given by this will be dt, will be dFF. That is a small frictional force into the radius of the wheel. So, that is a frictional torque applied by this small contact force of pressure P. So, that is a basic principle of brakes. That is, brake is mainly based on the frictional principle only. the moment of this frictional force relative to the point of motion contributes to retardation of motion, and this is how the mechanism of brake principle, brake working, is shown here. Now when we come to design and analysis of brake, how do we do a design? What are the parameters of interest? So now we will come to design of brakes. So before coming to this, I would like to stress one point, that whenever we are doing a braking action, we are bringing a body which is at motion, we are trying to retard the motion, or we are trying to bring it to a state of rest. So initially if a body is moving with velocity v1, and by the braking principle the velocity comes back to v2, because of change in velocity it has got a change in kinetic energy. Kinetic energy of the moving member is lost by retardation, and this energy is converted to heat due to friction. So what is the kinetic energy lost in this process? Kinetic energy lost will be given by half m into v1 square minus v2 square, where v1 is the initial velocity of the moving member and v2 is the final velocity of a moving member. Or if it is a rotating body which is rotating with the angular velocity omega 1, and due to this braking applied, its angular velocity comes down to omega 2, then the kinetic energy lost in this process will be given as half I into omega 1 square minus omega 2 square, where what is I? I will be the mass moment of inertia of the wheel of rotating body. I is the mass moment of inertia of the rotating body, omega 1 is the initial angular velocity, and after applying the brake, the angular velocity of the wheel comes down to omega 2. Then the kinetic energy lost in this process is given by half into I into omega 1 square minus omega 2, or this I, moment of inertia, can be written as m k square, where k is the radius of gyration. Then I can write kinetic energy lost is equal to half m k square into omega 1 square minus omega 2 square. This is the kinetic energy lost for a rotating body when the angular velocity comes down from omega 1 to omega 2. And usually when in braking action, this amount of energy which is lost is converted into heat, which results in a temperature rise of the body. And when we come to design and analysis of brakes, there are some parameters which we are interested. That is, performance of this device can be assessed on the basic knowledge of some of the following parameters. That is, for design and analysis of a brake, some parameters are of interest. One is braking torque, then we have actuating force, that is how much actuating force is needed to bring the body to rest. Then what is the energy lost? And we have seen this energy loss is converted into heat, so therefore what will be the temperature rise? Of the rotating body. So these are the parameters of interest in design and analysis of brakes. Now we will come to mechanical brakes. Mechanical brakes, there are basically two types. One is the drum brake, one is the disc brake. In this chapter on brakes in machine design, we will be dealing with the design and analysis of drum brakes. So a drum brake basically consists of a rotating body called a drum. A rotating body called the drum, whose motion is braked together with a shoe mounted on a lever, which can swing freely about a hinge axis H. That is, there will be a rod like this, which will be moving about a hinge H, and this will be applying force onto the rotating body by means of some shoe, and I will be applying a force in this direction F. So because of this contact between these two members, due to the friction generated due to this contact, the rotating body comes to rest. This is how the drum brake works. Now, the actuating force applied on the shoe gives rise to a normal contact pressure. That is, when I apply a force here, this will result in a normal contact pressure over this much area, and a corresponding friction force is developed between the stationary member and the rotating body, because when the normal force is acting on a body and one is stationary and one is rotating body, because of this normal force a friction force gets generated, and the friction force will be given by the coefficient of friction times the normal reaction, and this friction force tries to retard the motion of the drum, and this friction force causes a braking torque about the center of the drum. This is given by the braking torque of the brake. Now, this drum brake can be divided basically into two types. Now, this member which comes in contact with the moving body is called the shoe in a brake. And now the drum brakes are basically classified on the shoe geometry. It is divided into short shoe and a long shoe. So, what is the short shoe and what is the long shoe? What is short shoe and what is long shoe? Short shoe, as the name indicates, it's a short shoe. That is, the length of the shoe is less, and the area of contact becomes less. This area of contact is less, hence the contact pressure is uniform. We have seen that when the shoe is pressing against a moving body, a contact pressure is generated, and this contact pressure results in a frictional force, which will be given by mu times the contact force, and this frictional force causes a braking torque about the center, which tries to retard the moving body. So, when the length of the shoe is less, the contact pressure remains uniform over the length of the shoe, and when the area of contact becomes large, the contact may no longer be with a uniform pressure. That is, for the long shoe, the area of contact is large, and assumption of uniform pressure is no longer valid. Assumption of uniform pressure will no longer be valid. For a long shoe. So, that is the basic difference between a short shoe and a long shoe. In our design and analysis of mechanical brakes, we'll be concentrating more on the short shoe design and analysis. Now, we will see the analysis of short shoe. So, short shoe, we know it's called a short shoe because the length of the shoe is less, and the basic assumption is when the length of shoe is less, the area of contact is less, and the pressure variation across the area of contact is negligible, or we can assume that the contact pressure will be uniform over the entire area of contact. And this figure shows a brake shoe mounted on a lever hinged at point O. This is a point O, and now we are applying it to when this is rotating in this anti-clockwise direction. To bring this wheel to rest, we have to apply a braking force, and now we have to apply a braking force in this direction of value Fa. This is the actuating force or the braking force. So, we are going to find what is the value of this actuating force required to bring this to rest. Now, when I am applying an actuating force in this direction, this shoe comes in contact with the rotating wheel, it comes in contact with this rotating shoe, it will be applying a force which will be P into dA, and because of this a normal reaction will be generated onto the brake shoe, which will be in this direction, and the friction force acting on the wheel will be in this direction, because the wheel is rotating in the anti-clockwise direction. Therefore friction always acts opposite to the direction of motion. So this normal reaction caused by the braking shoe on the moving wheel causes a friction force which tries to retard the motion of the wheel. And what will be this friction force? It will be mu times the coefficient of friction times the normal reaction acting on the wheel. That will be the friction force acting, and the friction force acting will tend to produce a torque about the center of the wheel, which will be given by this friction force multiplied by the radius of the wheel, and this will be the braking torque which will be acting to stop the wheel. So the moment of this friction force about the drum center constitutes the braking torque. So that is the basic principle of working of the brake. Now to analyze this, we'll try to draw the free body diagram of the brake shoe, and we'll show what all the forces acting on this brake shoe. Now this is the free body diagram of the brake shoe separately, and the wheel is not considered here. Now as I have told earlier, this is the actuating force which is applied at this point of a lever which is hinged about the point O here. And since this, what is this joint? This is a kind of a hinged joint. We have seen that in a hinged joint there are only two reactions, that is reaction force in x direction and y direction alone. There will be no moment reaction because it is free to rotate about this axis. When the motion is constrained, then only reaction force will be acting on it. So this is the actuating force which we are applying, and this is I told that when we are applying an actuating force, this pressure into area will be acting on the wheel, and the wheel will be exerting an opposite reaction which will be the normal reaction, which will be acting on the brake shoe, which will be in the opposite direction. This will be normal direction. And what is the frictional force acting on the brake shoe? We know the friction force acting on the wheel is in this direction. Therefore on the shoe an equal and the opposite force will be acting. So friction force on shoe will be in this direction, towards left. That is shown in this way. And this friction force will be given by mu times this normal force. And now we will try to find what will be the value of this actuating force required to stop the wheel. For that we need to use the static equilibrium equation and get the equilibrium, write down the equations of motion and find the unknown. Now we will try to do the analysis of this short shoe, and I have told that this is only equilibrium equations we have to find out. Now this is the actuating force Fa, which is acting at a distance of A from the hinge location, and this is the brake shoe which is acting on the wheel, and the Fn is a normal reaction acting on the brake shoe by the wheel, and due to this normal reaction there will be a frictional force acting on the wheel. Therefore this frictional force on the shoe will be opposite in direction to the frictional force acting on the wheel because of Newton's third law. And the reactions at the hinge are Rx and Ry. Because it is a hinge, we have only the reaction forces, there is no reaction moment. Now what we have to do is we have to find what will be the value of this actuating force and other unknowns. So now we write down what are the equilibrium equations. We have the basic equilibrium equations are sigma Fx is equal to 0, sigma Fy is equal to 0, and sigma Mz equals 0. So what does this equation give? The first equation, sigma Fx equals 0. This gives that Rx, that is one force acting in the positive direction, another force is Ff, that is in minus direction. So minus Ff equals 0, or which gives the horizontal reaction is nothing but equal to frictional force acting on it. Now the second equilibrium equation, sigma Fy equals 0, gives what are the upward force? Upward force is Fn, and what are the other force? Downward forces. Fa, it's minus because it is acting downwards, and Ry is also acting downwards, so that is also Ry is equal to 0, which gives that Ry equals Fn minus Fa. Now sigma m about any point will be 0, so we will take the moment about the point O. So what does that give? That gives the moment due to the moment about this point due to the force Fa will be in the anti-clockwise direction. So usually moments in the anti-clockwise direction is taken positive and clockwise direction is taken as negative. So what are the forces here? We have Fa, Fn and Ff. So these three forces will be causing moment about the point O, and there will be no moment due to Rx and Ry because they are passing through this point. So what are the moment, what does this equation give? The moment equilibrium equation, that gives Fa into A, that is in the clockwise direction, so it is positive. Then what about Ff? That will be creating a moment of Ff into C, that is also in the anti-clockwise direction, so that is also positive, plus Ff into C. What is the other force acting? Fn. So Fn will be creating a moment of Fn into B about the point O, but it is in the clockwise direction, so it will be negative. So it will be minus Fn into B equals 0. Or we get Fa equals Fn B minus Ffc divided by A. So this will be my actuating force. And what is F in terms of Fn? We know that friction force is equal to mu times the normal reaction, is Fn. So this I can write as B minus mu C divided by A into Fn, be my actuating force. So my actuating force will be B minus mu C by A, where everything are geometric parameters. B is the distance between this point and the hinge point. The normal force and the hinge point is B, and the A is the distance of the actuating force from the hinge point, and C is the distance of the frictional force from the hinge point, and Fn is the normal force acting on the rotating body. So this is the actuating force. Now from this we can bring out some conditions. So what is this condition? B minus mu C by A. This can be positive, this can be negative, this can be 0. So we have three cases. So we have seen that actuating force required to stop a moving body is given by B minus mu C divided by A into Fn. Then B, A and C are geometric parameters which we have seen earlier, and mu is the coefficient of friction between the shoe and the rotating body. Fn is the normal force acting on the V. Now we have three cases here. Case 1, when B is greater than mu C. If B is greater than mu C, what will be Fa? Fa will be a positive value. A is positive, and what you can get from this equation? F is equal to B minus mu C into Fn. So when this B becomes greater than mu C, that means frictional force is there, and it is trying to reduce the actual actuating force. If the mu C value is higher, B minus mu C value will become lower and the actuating force becomes less. That is, Fa is always positive, and mu C, when mu C keeps on increasing, your B minus mu C keeps on decreasing, or your actuating force keeps on decreasing. So in this case, the frictional force tends to reduce the magnitude of actuating force. Therefore I can say force tends to reduce the magnitude of actuating force. Such kind of a brake is called partially self-energizing brakes. So such kind of brakes where the frictional force tries to reduce the magnitude of actuating force is called as self-energizing brakes. But in this case, the brake is not self-locking because you need some force, some actuating force is required to bring the wheel to rest, or some actuating force is required for braking action. Therefore, it is called as self-energizing brakes, because as you apply more force, your friction force increases and it tries to gives more energy to brakes and increases the effectiveness of brakes. So such kind of brake is called a self-energizing brake. Now we have a second case 2, where B is equal to mu c. In that case, what about Fa? Fa will become 0. That is, there is no actuating forces required to bring the body to rest, or such kind of a brake is called as fully self-energizing or self-locking brakes. Here, no actuating force is required. In this case, no actuating force is required to bring the body to rest. It will automatically come to rest because of this frictional force. Such kind of brake is called a self-locking brake. Therefore, for condition of self-locking B should be equal to mu c, and for self-energizing B should be greater than mu c. And the third case is there, that's the most dangerous case, where B becomes less than mu c. This is a case that is when Fa becomes negative, or this becomes a kind of a uncontrolled braking. That is, this kind of, it's difficult to visualize this kind of a situation, but this is called a this is a case of a uncontrolled braking, where your actuating force becomes negative. So in always when designing the short shoe brakes, care should be taken to see that brake is not self-locking. At the same time, the full advantage of partial self-energizing effects should be taken. So it should be a partial self-energizing brake is the optimum condition of brake. Therefore, the optimum condition to avoid the self-locking, of brakes, therefore to avoid self-locking of the brake, the condition should be that B should be greater than mu c. This is a condition to avoid self-locking. These are partially self-energizing brakes. Partially self-energizing brakes are ones where your frictional force is acting on the brake and it is aiding your actuating force, or it tries to reduce the magnitude of the actuating force, but actuating force will be always positive. Some actuating force will be required. So that is about the design and analysis of short shoe brakes. So we'll try to solve one problem on short shoe brake. So a simple band brake is to absorb 4.5 kilowatts at 150 rpm. The coefficient of friction is given as 0.12, and the maximum pressure between the lining and the drum is 700 kPa. Determine the width of the band if the drum diameter is 300 mm and the angle of wrap is 215 degree. So before coming to this problem, we will see about the band brakes initially. Now we will consider another kind of brakes called the band brake. Okay. A band brake consists of a flexible steel strip lined with friction material which is pressed against a rotating disc. This is a rotating brake drum, and this is the flexible steel strip lined with the friction material. This will be pressing against the rotating drum, and because of this friction, a retarding torque is applied on this wheel and it comes to a state of rest. when one end of the steel band passes through the fulcrum of the lever, fulcrum of the actuating lever, this brake is called a simple band brake. And that this is the figure of a simple band brake. Here the main how to find out the tensions in this brake. Now for this band brake we have some relations. If P1 is the tight side and P2 is the slack side, and mu is the coefficient of friction and theta is the angle of wrap, that is the flexible steel strip is in contact with the rotating drum from this point up to this point. The portion of the drum over which this is in contact with this drum is called the angle of wrap. So here I will write P1, see tight side tension, and P2 is a slack side tension, mu is the coefficient of friction, between the friction lining and the brake drum, and theta is the angle of wrap. If this is the case, then we have P1 by P2 equals e power mu theta. This is the first relation we have for band brakes, and the retarding torque Mt is given by P1 minus P2 into R, where R is the radius of the brake drum. So radius of the brake drum. Now taking the moment about this hinge point, we get that P2 into A is equal to P into L, or we get the P is equal to P2 into A by L. So these are the main relations we will have in a band brake, simple band brake. So this is called a simple band brake. It's called a simple band brake because one end of the steel lining is passing through the fulcrum of the actuating lever. So in this case, the ratio of the tension in the tight side to slack side is given by e power mu theta, where mu is the coefficient of friction between the lining and the brake drum, theta is the angle of wrap, and the retarding torque or the torque absorbed by the brake is given by P1 minus P2 into R, and P is given as P2 into A by L, where A and L are the dimensions, linear length dimensions, and P2 is the slack side tension. So this is about the simple band brakes. Now there is another type of brake called the differential band brake. Now we will see about the differential band brakes. So now we will see about another type of band brake which is called differential band brake. It's called differential because it's not simple band brake, because the two ends of the steel strip are getting connected to the levers and none of the ends are connected to the fulcrum. So it's called a differential band brake because both the tensions, the tension in the tight side as well as tension in the slack side, contribute to a moment about the hinge point. Now here also we have the relation, that's P1 by P2 is equal to e raised to mu theta. Here theta will be equal to 180 degree. Now if we take moment about the hinge point, we get P into L minus P2 into A plus P1 into B equals 0, or P equals P2A minus P1B divided by L. Or substituting this in substituting this equation in this we get it as P2 into A minus B e power mu theta divided by L. Therefore, as we have seen in the drum brakes, here also we can, where P is the actuating force. So this actuating and force can be positive, negative or 0 depending upon this value. So we have again three cases when A is greater than B e power mu theta. It's called a energizing brake. Brakes. And for self-locking of the brake, we should have A is less than or equal to B into e power mu theta for self-locking. This is the condition which we have seen earlier also. So you can write A by B should be equal to e power mu theta for self-locking of this brakes. This is a condition for self-locking of a differential band brake. In this relation, we are getting P into L. P into L is this clockwise moment, and minus P2 into A because the tension acting is this way. Therefore, force acting on this lever will be directed this way. So your P1 and P2 will be acting like this on the lever. Therefore, we get, when you take the moments, it will be P1 into L, P into L plus P1 into B minus P2 into A will be equal to 0. So that's how we get the actuating force in terms of one of the tensions. Can be a slack side tension or a tight side tension depending upon the direction of rotation. So that is about the brakes. We will try to solve some problems so that we can better appreciate the importance of these concepts. Now we will see a simple example. A simple drum brake is to absorb 4.5 kilowatts at 150 rpm. The coefficient of friction is 0.12 and the maximum pressure between the lining and the drum is 700 kPa. Determine the width of the band if the drum dia is 300 mm and the angle of wrap is 215 degree. Now we are given that the power absorbed is given by 4.5 kilowatts as equal to 4500 watts, and power absorbed will be given by 2 pi nt by 60, where T is the torque, N is the RPM. So from this we can get your braking torque T will be given by 60 P by 2 pi N. That will be 60 into P is 4500 divided by 2 pi into 150 rpm. So what is this? 60 into 4500 divided by 2 pi into 150. This will be 286.5 Newton meter. Now this is the braking torque given. So what is this braking torque in terms of the frictional force? This braking torque is given by mu times the normal reaction. What is the normal reaction? It will be pressure into area. That is, so if this is the drum, so suppose if this is area, this suppose we will assume that this is the area. This is the contact pressure is P. So the area of contact will be the torque will be mu times the normal reaction. Normal reaction is pressure into the contact area. Contact area will be pi into D if it is a full wrap, but it is wrapped only 215 degree. So out of 360 degree it is wrapped 215 degree. So pi D into this fraction will be the length of this. For the area we need this also into width. So this will be the braking torque. So we'll substitute the values. 286.5 is equal to mu is 0.12 and the pressure is 700 kilopascal. 700 into 10 power 3 into pi into what's the diameter given? Diameter is 300 mm. 300 mm. So we'll make it in meters. So 300 by 1000 into 215 by 360 into W. So we get W in terms of meters. So what does this give? 286.5 divided by 0.12 into 700 into 10 power 3 into 1000 into 360 divided by pi into 300 into 215. This will give W as 6.1 into 10 power minus 3 meters, or given as 6.1 mm. So in for design case we can take it as 10 mm. So width of the band should be equal to 10 mm for this case. So this is one of the application of the principles we have learned in drum brake. So we will see another problem here. In a band brake, the ratio of tight side tension to the slack side tension is 3. The angle of overlap of the band on the drum is 180 degree. Sorry, this is not 18. This is 180. What is the coefficient of friction? Now we know in a band brake, the ratio between the tight side tension P1 to the slack side tension P2 is given as E per mu theta. So how we can in a band brake, the ratio of the tight side tension to a slack side tension is given by E power mu theta, where mu is the coefficient of friction and theta is the angle of overlap. In this problem, we are given this ratio and we are asked to find out what is the coefficient of friction. So this is then the direct substitution. So P1 by P2 is equal to E per mu theta is given as 3. So what is the value of mu if theta is equal to 180 degree? So how do you find it? Now take natural logarithm on both sides. So we get ln of E per mu theta is equal to ln of 3. And ln of mu theta will be equal to mu theta is equal to ln of 3. And what is theta? Theta is equal to 180 degree. Here it will be pi radians. Therefore mu will be 1 by pi times ln of 3. What will be this? Ln of 3 divided by pi. This will be 0.35. The coefficient of friction will be 0.35. This question was asked in GATE 2003. So this way we can easily solve the problems related to the band brakes. Now we will see another problem. A band brake which is shown below consists of a lever attached to one end of a hand. The other end of the band is fixed to the ground, shown here. The wheel has a radius of 200 mm and the wrap angle is 270 degree. The braking force applied to the lever is limited to maximum of 100 newtons. The coefficient of friction between the band and the wheel is 0.5. Now what will be the maximum tension in the band and what is the maximum wheel torque? Now how do we do this? Now if suppose this tension is given as P1. Now if you take the free body of this lever, it will be can be drawn as force of 100 newtons applied here and force of P1 here and this is the hinge point. So this is 1 meter, this is again 1 meter. Therefore, taking moments about the hinge point, what we get is P1 into 1 is equal to 100 into 2. Therefore, P1 is equal to 200. Now, suppose if P1 is the slack side for this band brake, then we have the tight side tension P2 to slack side tension is given by e power mu theta. That's only e power mu is given as 0.5 and theta is 270 degree. So it will be in radians 270 into pi by 180. So this will be how much? E power mu 0.5 into pi into 270 divided by 180. This will be 10.55. P1 is already we got it as 200. So for P2 will be this into 200. This will be 2110 newtons. So maximum tension will be 2110 newtons. Now what is the maximum wheel torque that can be completely braked? The maximum braking torque will be given as the tight side tension minus slack side tension into R. So here it will be 2110 minus 200 into 0.2. So this will be minus 200 into 0.2. This will be 382 Newton meter. This will be the braking torque which can be applied on this wheel due to the band brake. When 100 Newton is applied, the braking torque applied on the wheel will be 382 Newton meter. This was also asked in a GATE paper, GATE 2005. So you can see that once the concept of brake is clear, then all problems can be easily solved by applying the proper equilibrium equation and also solving the equations. And only thing is you have to remember what are the basic equations which we have derived for this band brake, basically the simple band brake and differential band brake. Similarly, in the drum brake also see what are the relevant equations, and only thing in whatever you learn here is nothing but static equilibrium equations only. So if you are able to draw the free body diagram and get the static equilibrium equations, I think we can solve any kind of a problem. So so that is about the brakes. So with that we come to the end of this chapter 1 in module 5 on brakes. This chapter on brakes and clutches will be done in 2 parts. The part 1 will be brakes and part 2 will be clutches. So with this we are completing with from here till here we will be completing this part 1 of this chapter, meaning basically the brakes. In part 2 we will be seeing about the clutches. Thank you.